I will start by giving my PhD presentation entitled Pulp Strength Enhancement by Oxygen Lignification. And I will start by giving you this picture. I think we all would like to have this picture as a representation of our planet, a healthy and sustainable planet. But this is not the full picture. We know that pollution and excessive uses of natural resources are a big challenge and leads to very big sustainability issues. So research is fundamental to try to provide better and more sustainable processes for our future. And one of the main important sustainable materials in our forest is wood. Wood is a three-dimensional anisotropic material with a well-organized structure and is mainly composed by three components: cellulose, hemicellulose, and lignin. And there are a lot of different products that you can produce from wood. My project is about for paper-based products. So in that case, we normally do pulping processes to remove lignin. So this picture here in the middle represents the fibers in the wood matrix. With the pulping process, the chemical one, we intend to remove the lignin that is gluing the fibers together in order to individualize them. So in most cases, we want to remove lignin, but how much lignin we want to remove, it will depend on the process and the final properties in the product that we want to produce. And we can look at lignin as the brown component in our product. So if you go shopping or if you have packagings, you have brown products. So you have some lignin inside the products. If you have writing papers, you don't have so much lignin inside. That's why it is white. And because I'm used to it, I probably will talk a lot about kappa number. But kappa number is basically the lignin content inside the fibers. So it's the same. If I talk about high kappa number, it means that the product is darker because it has more lignin. And the delignification degree is related to the process. So if we have a longer delignification degree, it means that we removed more lignin during the process. And now, very briefly, I will try to explain how the chemical pulping process works. So we start from the wood, we cut it in small pieces, and we feed a big digester with high temperature and chemicals. And in this step is known as the cooking of wood. It's the cooking step. And the most used and known one, and the one that I will also talk about here today, is the kraft cooking. And here you can remove the major part of the lignin. But, as I said, depending on the final products, the final properties, you might need other processes. Oxygen lignification is one of them. And by the title of my thesis, you already know that this is the main topic of my presentation. Oxygen can remove lignin and can also give very special properties to the pulp fibers, as I will show you later on. And finally, to have these bright papers, the printing papers, tissue papers, we normally have bleaching sequences, where we use different bleaching chemicals in order to selectively remove lignin, because lignin is more difficult to remove when you have lower contents. So during this process, lignin the lignin content is decreasing like this. And then we have the paper or the pulp part section. And as Christine said, kraft pulping is a biorefinery. So we also can recover the chemicals that we use from the cooking and produce energy from the lignin that we are removing in the process. But I will not talk about this. I will focus on kraft cooking and oxygen lignification. And as I said, kraft cooking can remove the major part of the lignin, up to 90%, by fragmentation and solubilization of the lignin. And if we look at this picture, is the fibers inside the wood structure. So by doing delignification, we remove part of the middle lamella, that is mainly lignin, and we can individualize the fibers in order to produce a lot of different products with different properties. So this is how individualized fibers look like in a microscope. But we can remove a lot of lignin in kraft cooking, but we cannot remove all of them because of the selectivity. When you start the cooking, the selectivity is high because you have a lot of lignin and it's very easy to start to remove it. But during the process, the selectivity is going down. And the selectivity is how much lignin you can remove without degrading the other components that are in the fibers, like cellulose and hemicellulose. And for that, we have oxygen lignification. Can still remove lignin. And with the alkali that we introduce in this process, the phenolic groups that are formed during the kraft cooking have a reaction, form a lot of different species that will oxidize and remove lignin. And also one special property that oxygen lignification has is the introduction of carboxylic acid groups by these oxidation reactions. And these carboxylic acid groups, also known as fiber charges, will give very special properties to our final products. And let me try to explain you how the fiber charge is changing from the wood that we have in our forest until the processes that I just showed you. So in native wood, we have a lot of fiber charges, and the fiber charges you can see here are the blue dots. Mainly in hemicellulose, in the silence. But during the kraft cooking, which the aim is to remove the major part of the lignin, and you are also removing some of the other components as well, the tendency is to decrease the fiber charges. So you lose fiber charges during the cooking for lower kappa numbers, lower lignin contents. One example is the reaction of the hexenuronic acids formations that occur during the kraft cooking. They both have fiber charges, these groups here, but during the process, the tendency is to dissolve them, and you will lose them in the end. In the other case, if you do a kraft cooking to a higher lignin content, you don't take so much of the components, and then you can do oxygen lignification and oxidate the rest of the components that you have in the fibers. So looking at these two pictures, you have similar lignin contents, but the one that has oxygen lignification process has a much higher content of fiber charges. And this slide is very important, so try to keep it in mind because I will bring it over again. When I started my PhD colleagues were asking me, why are you researching in pulping, oxygen lignification, paper production? This is something that is already known for so many years, is already well developed. What else do you need to improve? And of course, it's a very old process. We know a lot about it, but we can always improve it. And one of the big advantages with this is that we already have the major part of the companies that use kraft cooking and oxygen. We already have the equipment. We already have the process, the knowledge. So there is no need to invest in new equipment or invest in new processes. You already have all that you need there, but you can improve it in a very simple way, as I will show you. This is examples of how the pulping process have changed during the time. So in the beginning was much more kraft cooking and bleaching. And bleaching, if you remember, is the part where you remove lignin, almost no lignin in the final product. And is one of the most negative processes in the pulping process because it releases a lot of toxic compounds to the environment. So oxygen was introduced between these two processes as a way to decrease the bleaching. And then one of the main components that were used in the bleaching, chlorine, was abolished. So there was a very big need to increase kraft cooking in order to decrease the lignin content that would um, that would enter the bleaching part in order to reduce it, in order to decrease this environmental impact. But this is not really the best solution, because if you remember, the selectivity is not the same. So if you prolong too much the cooking, you are losing selectivity. You are degrading also the pulp, and you are losing yield. And yield is how much pulp you can take it from your process to the final product. Because with the pulping process, the chemical one, you have a yield around 50%. That is 50% of your material is not used for the product. So if you are reducing even more the yield, it's not so good. So this was a little back. So the kraft was reduced again. The oxygen was a little bit increased, but as you can see, oxygen was never the main point here. The point was decreasing bleaching. And in my PhD, I looked at oxygen lignification. So the approach that I used was to reduce kraft cooking to very high kappa numbers, very high lignin content, sorry, and do oxygen lignification in an extended way, and try to understand the potential that we can have from this process. And also, my PhD intends to change some mentalities, because do we really need bleaching for all the products that we use nowadays? Maybe we don't need. There is so many products that we can use it as a brown color and not white. So I also intend to change a little bit and imagine that we can produce products with similar or improved properties, but with less energy and also less chemicals. I think we can do that. So stay until the end of the presentation to understand how. So the main goal of my PhD was to provide a better understanding of oxygen lignification and its potential to modify pulp properties, and in particular pulp strength, because it's one of the main properties for the final products. But during my PhD, I also had other PhD research topics. So I started with this too, comparing kraft cooking with oxygen lignification. And here I studied a lot fiber charges, fiber swelling, pulp strength, of course, because this is the main goal, and also fiber morphology was one of the main topics that we saw that was very important to study. So the three first papers are very much about this. And the new thing here, different from the other studies in the old days, is that we are comparing oxygen lignification to similar lignin contents from the kraft cooking. We are not looking at the oxygen as a following step. We are comparing both at the same or similar lignin content. And then we had other topics like impregnation. The impregnation is the step before the cooking that promotes the diffusion and the penetration of the cooking chemicals inside the wood chips. And this is very important. And one of my supervisors, Elisabet Brännvall, have shown that if you use a high alkali impregnation, you can save the yield. So you can save more wood in your process. And we did this study together with oxygen, and we tried to look at the yield and the strength. So in the first topic, we saw that oxygen could improve mechanical strength. In the second topic, we wanted to see if the strength was maintained after this high alkali impregnation, and if the yield that you can increase with the high alkali impregnation was still preserved after the oxygen. So the new part here was the oxygen lignification. And then, as a natural way of going in the process, we evaluated basically the same thing after bleaching. And here we looked at the yield and some pulp properties like brightness. And now, in the end, we are evaluating the fiber nanostructure. We are trying to understand if there is any difference between kraft cooked fibers and oxygen fibers in the nanostructure level. And this will be the last manuscript. So I did a lot of different research topics, but I will only focus on the main goal here. And I will show you 4 examples of my trials. I did 4 kraft cookings with same chemistry, but I stopped in different lignin contents. And then I did oxygen lignification to the similar lignin content as the first one. So we can say that this trial here is our reference, and then we have other 3 trials that will be our comparison to the reference. They all have similar lignin contents, and you are producing the samples with a slightly different procedure, a short, a medium, and extended oxygen lignification. Then I did PFI refining, and refining is the mechanical treatment that you do in the fibers in order to promote the bonding between them. And if you remember this picture that I showed before, now I will give you examples, real examples of what is going on. So these 4 kraft cooking trials that I did, if you look at the graph, we have the total fiber charge, that is the same of acid carboxylic groups that oxygen can introduce, and the kappa number, that is lignin content. So looking at this target kappa number, and as this is our reference trial, we can see that we have different fiber charges if you stop the cooking in different lignin contents. And then if you do oxygen lignification, you will increase these fiber charges even more. So the first thing here is you can see that different lignin contents from the kraft cooking will give you different starting points. And then with oxygen, you can increase these fiber charges, and the higher is the charges, the higher will be the final result. And if we are comparing to this reference trial here, we have a big increase. We have this increase, and this. And you can see that the longer is the oxygen step, the higher will be the final total fiber charge. And this is very important for the mechanical strength. So this is directly related with the tensile index. Tensile index is the property that is mainly used to evaluate the strength of the papers. And we did the first trial, we got this total fiber charge, and we evaluated the tensile index here along the PFI revolutions. And the PFI, as I said, is the mechanical treatment, so the higher you do PFI, the higher will be the strength, because you are promoting these bondings between the fibers. And then we did another trial with the oxygen lignification. In this case, we improved 50% the fiber charges, and look closely what happens here in the tensile. Nothing happens. There was no increase at all. And this was quite disappointing during my first year, because I wasn't expecting this. So then we did other trials with a more extended oxygen lignification. We got around 70% higher charges, and in this case, we were able to get 6% increase. That is not bad. But then we did the other trial with a higher kappa number from the cooking and a more extended oxygen lignification. In this case, we got almost 90% of the fiber charges increase as the reference one. And we got 14% higher tensile index. So we are producing stronger papers with this extended oxygen lignification. And we have different, not steps, but we have different ranges. You can see that if you increase not so much, you have a low increase, medium increase, and high increase. And this will be directly related with the tensile index, that you will not have any improvement, or a medium improvement, or a high improvement. So this is very important. And also one slide that I think is very interesting, especially for industry, is that we show the same results along the tensile index with the structural density. Because in order to evaluate the product, we should evaluate to the same density. So if we have a specific density, let's say similar sheet density for these pulps, we can see that we have slightly higher strength, but with 50% less energy. One with the extended oxygen lignification only needs 2000 pfi revolutions, while the kraft cooked pulp needs 4000 pfi revolutions. So we have energy saving for the same strength. This means that oxygen lignified fibers have higher flexibility and conformability. That's why we get higher density without the need of so much high refining. And this is also extremely related to the fiber swelling. And the fiber swelling can be seen as the water retention value in this graph. You have the water retention value here, the PFI revolutions here, that is also tends to increase with the mechanical treatment. And these are the total fiber charge. So the higher the fiber charges, the higher will be the fiber swelling. And the picture here intends to illustrate what is happening inside the fiber. So you will have a swelling of the fiber inwards through the lumen. And this external part here is the fiber cell wall that will increase, that will take more water, and this is also called as internal fibrillation. That is provoked by the fiber charges and also from the mechanical treatment that we do with the refining. If we try to look inside the fibers, this is how it looks like. So the lamella starts to separate more and more, and that's why you get a higher increase, and also the fibers get more flexible. And this is how it looks like a real fiber. And we already saw that the increase in the fiber charges increase the swelling. That leads to the increase in flexibility and conformability of the fibers. And this also will lead to a higher fibrillation in the PFI refining. In the picture you can see here the external fibrillation. So it's the fibrils that are peeled off from the fiber that will promote more bondings in the paper. And that's why we can increase the mechanical properties of our product. As brief conclusions, we saw that extended oxygen lignification leads to higher fiber charges. In our case, we saw up to 90% higher when you compare to the kraft cooking. This leads to higher fiber swellability and flexibility, and of course leads to higher tensile index, better mechanical properties. In our case, was up to 18%. And a very special property as well, not property, but conclusion, is that we can decrease the refining energy up to 50% for the similar sheet density. What could be the future applications with this approach? We have several. Think about sack papers, stronger papers with less energy. You don't need so much refining. You don't need so much cooking. Or imagine high absorption products. You have a high fiber swelling, so why not take this as an advantage and use for tissue or hygienic products that you can also remove the bleaching part that will save you a lot of money. And with this, I think I can come back to the first picture and say that we can improve sustainability because we can have improved pulp properties with less energy, with also improved yield with oxygen lignification and high alkyl impregnation as well. I didn't show, but I tell you that we have improved yield, and we can have new opportunities for new products. I would like to acknowledge my supervisors for all the support they gave me during these years. Very, very appreciated. I would like to thank Rice and KTH for this opportunity, also for all the funding that I got from my PhD. I would like to thank my friends and to my family and to Sweden for this opportunity. Thank you very much. And thank you to all of you that are here today. It means a lot to me. Thank you very much.